Hey everyone, welcome to The Explainer. Today, we are taking a deep dive into Shewanella algae. Just a heads up, all the information we're covering comes from a comprehensive literature review using a Gemini deep search. And if you want to check out the sources for yourself, they're all in the notebook document that accompanies this briefing. All right, let's get right into it with Shewanella algae. Now, the crazy thing about this emerging pathogen is that its true danger was hidden for decades because of a massive case of mistaken identity. Honestly, understanding this historical mix-up is the key to the whole story. So, this bug has had a real identity crisis. It was first found in some bad butter way back in 1931 and has been bouncing between names ever since. But the real turning point, the big aha moment, came in the 1990s. As our molecular tools got way better, we started to realize something was off. The bug we kept finding in serious human infections, it wasn't actually Shewanella putrefaciens. And get this, the scale of the mix-up was huge. When scientists went back and re-examined old isolates, they found that more than 80% of the severe infections they'd blamed on Shewanella putrefaciens were really caused by its more aggressive relative, Shewanella algae. That discovery completely changed the game. Okay, so that's the history. The big question is, how do we avoid making that same mistake in our labs today? Well, the good news is it's actually not that hard. The answers are right there on the bench. You know, a huge part of the problem has always been our automated ID systems. Think about it. If Shewanella algae isn't even in the system's library, what's it going to do? It sees this H2S producing oxidized positive non-fermenter, and it just spits out the only name it recognizes, Shewanella putrefaciens. But hey, we don't need to rely on the machines for this one. Some simple old-school micro will give us the right answer. And when you look at them side by side on the bench, the differences are just night and day. Yeah, the hemolysis can be a bit tricky. Sometimes it's weak or takes a while to show up. But check this out. Growth at 42 degrees Celsius and in a high-salt broth? Shewanella algae can handle the heat and the salt, while Shewanella putrefaciens just can't. These are simple, cheap tests that give you a really solid answer. So you can basically boil it down to this simple three-step process. You've got your classic profile, a gram-negative rod, it's oxidized positive, and you've got that beautiful blackening on your TSI from the H2S. From there, just set up two things, a plate incubated at 42 degrees and a 6.5% salt broth. If you get growth in both, you've got a really, really strong presumptive ID for Shewanella algae. Now, of course, for the final, definitive answer, you're going to want to turn to molecular methods. These are the gold standard. I mean, 16S sequencing is how we figured out this whole mix-up in the first place. MALDI-TOF is fantastic, it's fast, it's accurate, but, and this is a big but, only if Shewanella algae is actually in the database. You got to check. And for the really deep dives, like an outbreak investigation, whole genome sequencing is the way to go. All right, so we know how to spot it in the lab. But why is getting the name right so important? Let's talk about what this bug actually does to people. This thing can cause a whole range of problems, but there is definitely a pattern. The most common thing you'll see are skin and soft tissue infections, a lot of times after someone's been in seawater. But it can get much, much nastier. When it goes invasive, we're talking bacteremia, liver infections. It's almost always in patients who are already vulnerable. Think people with underlying liver disease, cancer, or diabetes. It's a classic opportunist. And this is where things get really tricky for the clinicians. Picture this. A patient with liver disease comes in with this awful, fast-moving skin infection after being at the beach. What's the first thing you think of? Vibrio vulnificus, right? It's the textbook case. But here's the kicker. Shewanella algae can look identical. It's a perfect mimic. And that is a huge problem because their resistance patterns can be different. Getting that ID from the lab and getting it fast is absolutely critical for treatment. Okay, so we've identified the bug. Now we have to treat it. And this is where it gets really tough. It kind of feels like we're flying blind. This quote really says it all. There is no official playbook for treating these infections. No specific guidelines from IDSA, EU-CAST, nothing. You can't just look up the right drug and dose. It all comes down to two things: what your lab susceptibility results say, and how well the surgeons can get in there and clean out the infection. But wait, it gets even more complicated. Just because the bug is susceptible on day one, that doesn't mean you're in the clear. This is one of those clever bacteria that can actually develop resistance during therapy. A drug that was working perfectly can suddenly stop working right in the middle of treating the patient. And this case study is the perfect and frankly scary example. So the patient has bacteremia. The initial isolate is susceptible to imipenem, MICF2. Great. They start treatment. But the patient isn't getting better. So they find a spinal abscess, they culture it, and boom, the new isolate is resistant. The MIC shot up to 16. That's an 8-fold increase developing right there, inside the patient. It's a huge warning sign, especially for these deep, hard-to-treat infections. So, to pile on yet another challenge, let's talk about breakpoints, or rather, the lack of them. As of the latest EU-CAST guidelines, there are still no official species-specific clinical breakpoints for Shewanella. And that makes our job in the lab so much harder. How are you supposed to confidently call something susceptible or resistant when there's no official line in the sand? So what do we do? Well, UCAST gives us a kind of roadmap for this situation. Step 1. Just report the raw MIC value. Don't even try to slap an S, I, or R on it. Then, you can compare it to what's called an EcoF to see if the bug is wild type. But the most important step is communication. You have to talk to the clinical team, explain the limitations, and clearly note on your report that there are no specific breakpoints, often using surrogate breakpoints with a big disclaimer. All right, so this bug is tricky to identify and tricky to treat. That means the best option is to not get infected in the first place. Let's talk about prevention, both out in the world and inside the hospital. Now, most of the time, people pick this up from the environment, seawater. But we can't get complacent. Hospital-associated outbreaks of Shewanella algae are a real thing, and sometimes the source is the last thing you'd ever suspect. This outbreak investigation is a perfect example, like something right out of an epidemiology textbook. They notice a cluster of infections on one unit. They do the detective work and find a link. All the patients had external drains. So they start sampling, and they find the culprit. A contaminated multi-use measuring cup that was being passed between patients to measure their drain output. The fix was just as simple. Switch to single-use cups and the outbreak was over. It's a powerful reminder of that basic infection control rule. One patient, one piece of equipment. So, what do we tell the public? For at-risk people, it really comes down to 3 common-sense things. First, if you have any cuts or scrapes, just stay out of seawater. If you can't, wash it out really well with soap and fresh water as soon as you can. Second, if you have a weak immune system or liver disease, please avoid raw seafood, especially oysters. It's just not worth the risk. And finally, for people who work on the water, like fishermen, wear your protective gear. Okay, for our last point, let's zoom all the way out and look at the really big picture here. Because the threat from Shewanella algae goes way beyond just one sick patient. It's part of a much larger global health issue. You see, Shewanella algae is basically a swimming library of antibiotic resistance genes out there in the ocean. And the scary part? It's carrying the ancestors of some of our worst nightmares, like the genes for OXA48-like carbapenemases. And through horizontal gene transfer, those genes can literally jump from this marine bug into something like Klebsiella pneumonia, a major ICU bad guy. So that leaves us with this final, really big question. If resistance genes can flow from the ocean right into our ICUs, what does that mean for us in the clinical lab? Our role is changing. We're not just diagnosing an infection in one patient anymore. We're on the front lines, acting as environmental sentinels, watching this massive global threat unfold. I really hope you found this briefing useful. If you've ever dealt with this organism in your lab, I'd love to hear about it. Drop your experiences in the comments. And of course, please subscribe for more deep dives like this one.